Welcome to section 8.4, compound interest. Objective 1, use compound interest formulas. Compound interest involves interest computed on the original principal as well as any accumulated interest. In other words, with compound interest, you earn interest on interest, which causes your money to grow faster than with simple interest. This is one of the most powerful concepts in personal finance. It's how investments grow substantially over time and why starting to save early makes such a big difference. If you deposit P dollars at a rate R in decimal form, subject to compound interest, then the amount A of money in the account after T years is given by the following formula. A equals P times 1 plus R to the power T, where A equals the future value or the total amount in the account, P is the principal, the initial deposit or present value, R equals the annual interest rate, of course, written as a decimal, and T is the time in years. So if your time is given in months, you'll have to convert it to years. The period of time between two interest payments is called the compounding period. So when compound interest is paid more than once per year, the compounding period is less than 1 year, and we need to adjust our formula accordingly. The frequency of compounding significantly affects how much your money grows over time. So here are some compounding frequency terms. So if the compound interest is paid once per year, the interest is compounded annually. If the compound interest is paid twice per year, so every 6 months, we say the interest is compounded semi-annually. If the compounding period is 1 month, the interest is compounded monthly. And if the compounding period is 3 months, the interest is said to be compounded quarterly. So if you deposit P dollars at a rate R, of course in decimal form, subject to compound interest paid in N times per year, then the amount A of money in the account after T years is given by the following formula, where A equals P times 1 plus R divided by N, all of that raised to the quantity N times T, where A is your future value, P is your principal, R is your annual interest rate as a decimal, N is going to now be the number of compounding periods per year, and T is your time in years. So some common values for N are N equals 1. We use this when our situation states that we are compounding annually because that's once per year. N equals 2. This is for when we're compounding semi-annually, so that would be twice per year. N equals 4. This is when we're compounding quarterly, so this would be 4 times per year. N equals 12. This will be when we're compounding monthly, so this will be 12 times per year. And N equals 365. So this will be for when we're compounding daily. So some banks use continuous compounding. So this is where the compounding periods increase infinitely. So after T years, the balance A in an account with principal P and interest R in decimal form is given by this formula. So this is the third formula regarding compounding interest. In this situation, E is a mathematical constant approximately equal to 2.71828. Okay, so it is a non-repeating decimal that goes on forever. It's similar to pi. This represents the theoretical maximum growth when interest is compounded infinitely often. Continuous compounding produces slightly higher returns than any finite compounding period, though the difference becomes smaller as the number of compounding periods increases. So daily compounding is very close to continuous compounding in practice. A key takeaway for this is that the more frequently interest is compounded, the more your money grows. This is why understanding compounding periods is crucial for making informed financial decisions about savings accounts, investments, and loans. So we've looked at 3 different formulas. Let's apply it to some problems so that we can see it in application. our first guided example here states that you deposit $1,000 in an account at a bank that has a rate of 1.4%. We are asked to find of the amount of money in the account after 5 years, subject to interest compounding once a year, and then round to the nearest cent. And then we also want to find our interest. Okay, so the interest that was tacked on to the principal. So first things that we need to do is find A. We need to find the amount of money in the account after 5 years. So we know P is going to be 1,000. We know R is 1.4%, which is 0.014. And we know T equals 5. We're asked to find A. So A here is going to be P times 1 plus R to the power T. Okay. So substituting in our values, we have 1,000 times 1 plus 0.014 raised to the power 5. Okay. So this will be approximately, rounded to the nearest cent, $1,071.99. Okay, so that is the amount of money in the account after 5 years. So our second problem is asking us, what is the interest? Well, to find the interest, we are going to take our future value and we're going to subtract the principal to determine how much interest was applied to our original amount. So we'll take $1,071.99 and subtract 1,000, and that will get us a total of $71.99. So that is the total interest that was added to the principal. All right, so we have a sum of $10,000 that's invested at an annual rate of 1.9%. To find the balance in the account after 5 years, subject to quarterly compounding and continuous compounding. Okay, so we want to perform both operations where we are quarterly compounding and continuously compounding. So let's first state what we know. We know that our principal is $10,000. We know our rate is 1.9% or 0.019. We know our time is 5 years. Okay. So for A, since we're compounding quarterly, our N is going to be 4. And for B, since we are continuously compounding, our N does not exist. It's not applicable for this problem. So for compounding quarterly, our formula will be A equals P times 1 plus R over N to the power NT. And for compounding continuously, our formula will be A equals P times E to the power RT. Okay, so let's substitute in our values for A. So we'll have 10,000, not 1,000, times 1 plus 0.019 divided by 4 raised to the power 4 times 5. Okay, that will give us a total of $10,994.12. Okay, then for B, we'll have 10,000 times E to the power 0.019 times 5. That will give us a total of $10,996.59. Okay, so if we needed to choose, although this problem doesn't state, it just asks us to find the balance. If we were to choose which one would be the better investment, we would say that the better investment is the 1.9% continuously compounded. So this one right here would be the better investment. Awesome. All right. Now, suppose that you have $12,000 to invest. Okay. Which investment yields the greater return over 3 years? Would it be the 4.15% compounded monthly or the 4.1% compounded continuously? Okay. So we know our principal, the one that we're starting off with, our initial amount, is going to be $12,000. Okay, that's how much we're going to be invested. We also know that we want to know our return after 3 years. So T is going to be 3. Now, option 1, we have an interest rate of 4.15%, which is 0.0415, and it's compounded monthly, so n equals 12. For option number 2, we have an interest rate of 4.1%, so that's 0.041. We're compounded continuously, so n is not applicable for this problem. Okay. So since we have a compounding rate here, compounding monthly for option 1, our formula is going to be A equals P times 1 plus R over N to the power NT. For option 2, we don't have an N, so we are compounding continuously. So our formula is A equals PE to the RT. Okay. So for the first one, we have 12,000 times 1 plus R, which is 0.015, divided by N, which is 12, times 12 times 3. Okay. Entering all of that in our calculator, we get a total value of 13,588 and 7 cents. Okay. For option 2, we'll substitute in our value. So we have 12,000 times E to the power 0.041 times 3. And our value is $13,570.61. Okay. All right. So which investment yields the greater return? Well, in this scenario, the investment that yields the greater return is the 4.15% compounded monthly. So this one yields the greater return. All right. Awesome. Objective 2, calculate present value. So sometimes in financial planning, you know how much money you want to have in the future value. And you need to figure out how much you should invest today to reach that goal. This is how much to invest today amount is called the present value. Present value answers the question, what amount of money today will grow to my desired future amount? So if $8 are to be accumulated in T years in an account that pays rate R compounded in N times per year, then the present value P that needs to be invested now is given by the following formula. Now, this formula is not a new formula. When we had our equation, A equals P times 1 plus R over N to the NT, all we did was take this part on the right-hand side and divide it on both sides to get P. Okay, so it's originating from the same problem that we worked with previously in the past objective. Nothing has changed. Okay. So in our first guided example, all right, it's asking how much money should be deposited in an account that earns 1.5% compounded semi-annually so that it will accumulate to $10,000 in 8 years. So here, our A, our future amount is $10,000. That's what we want it to reach. Our R is 1.5% or 0.015. Our T is 8 years, and we are compounding semi-annually, so N equals 2. So we want to find how much we should deposit today. So that would be P. So our formula, P equals A divided by 1 plus R divided by N to the NT. Substituting in our values, we'll have 10,000 in the numerator divided by 1 plus 0.015 divided by N, which is 2, raised to the power 2 times 8. Okay. When we enter this value in our calculator, we are going to get $8,873.18. Remember, we need to round up so that we have enough money to reach our goals. Okay, not round down. All right, how much money should be deposited today in an account that earns 3.5% compounded monthly so that it will accumulate $10,000 in 3 years? So we want to know how much we need to invest today. So that means we're trying to find P. Our A, the total amount in the future that we want to have, is $10,000. Our rate is 3.5%, which is 0.035. Our T is 3, and we're compounding monthly, so our N here is 12. Okay. We're going to use the same formula where we have A divided by 1 plus R divided by N raised to the power NT. So A is 10,000 divided by 1 plus 0.035 divided by 12 raised to the power 12 times 3. Okay. So when we enter that into our calculator, we will get the value $9,004.63. Again, remember to round up so that we have enough deposited in the beginning in order to reach our goal. Objective 3. Understand and compute effective annual yield. So the effective annual yield, or the effective rate, is the simple interest rate that produces the same amount of money in an account at the end of 1 year as when the account is subject to compound interest at a stated rate. In other words, it's a way to compare different investment options on an apples-to-apples basis, regardless of how often interest is compounded. Think of it this way. If you see one savings account offering 5% compounded monthly and another offering 5.1% compounded annually, which is better? The effective annual yield tells you the true annual return, making comparison easy. So suppose that an investment has a nominal interest rate R in decimal form and pays compound interest N times per year. The investment's effective annual yield, Y, in decimal form, is given by the following formula. Y equals the quantity 1 plus R divided by N raised to the power N, all minus 1. Okay? Now, the decimal form of Y given by the formula should then be converted to a percent to express the effective annual yield as a percentage rate. So Y is a rate. So that means it must be expressed as a percent. So Y is the effective annual yield. R is the annual interest rate, and N is the number of compounding periods per year. Okay, so this formula calculates how much $1 would grow in 1 year with compound interest, and then subtracts the original $1 to show just the interest earned. This interest amount represents the effective annual yield. The more frequently interest compounds, meaning a higher N, the higher the effective yield will be, even if with the same rate. So if you're selecting the best investment from 2 or more investments, the best choice is the account with the greatest effective annual yield. So when borrowing money, however, the effective rate or effective annual yield is usually called the annual percentage rate, or the APR, and you want the lowest APR possible. So for savings and investments, you want to choose the highest effective annual yield. For loans and credit cards, you want to choose the lowest annual percentage rate, okay? Because then you pay less on interest. Whereas in investments, you want a high APR, or effective annual yield, so that you get more interest added on to your investments. So the true takeaway is that the effective annual yield is the true interest rate that accounts for compounding. And always use effective annual yield when comparing investment or loan options to make the most informed financial decision. Okay. Alrighty. So in our guided examples here, okay, you deposit $6,000 in an account that pays 3% interest compounded monthly. We want to find the future value after 1 year, so we'll round it to the nearest cent. And then we want to determine the effective annual yield and round that to the nearest hundredth of a percent. Okay, so you deposit 6,000, so that's P, at a rate of 3%, so that's 0.03, compounded monthly, so N equals 12. For the first problem, we want to find the future value after 1 year. So in this case, our T equals 1. So our formula will be A equals P times 1 plus R over N raised to the power NT. Substituting in my values, I get 6,000 times 1 plus R, which is 0.3, divided by 12, raised to the power 12 times 1. Okay, so this comes out to be $6,182.51. Okay, so that's my future value. The second part of this problem tells me to find the effective annual yield. So Y equals 1 plus R divided by N raised to the power N minus 1. So I have 1 plus 0.03 divided by 12 raised to the power 12 minus 1, which equals 0.030415. Since I need to round to the nearest hundredth of a percent, okay, my percentage will be 3.04%. So that is the effective annual yield. Okay. All right, so what is the effective annual yield of an account paying 3.2% compounded quarterly, round to the nearest hundredth of a percent. So we know that our interest is 3.2%, which is 0.032. We're compounding quarterly, so n equals 4. Our formula for the effective annual yield is 1 plus r divided by n raised to the power n minus 1. So 1 plus 0.032, because that's r, divided by 4 raised to the power 4 minus 1 is approximately 0.032386. We convert this to a percent, we'll get 3.2386%, but it asks us to round to the nearest hundredth of a percent, which is where the 3 is. So this would be 3.24%. That's the effective annual yield of an account that pays 3.2% compounded quarterly. Okay. All right, so an account has a rate of 3.5%. We want to find the effective annual yield rounded to the nearest tenth of a percent if the interest is now compounded monthly. Okay, so our rate is 3.5%, which is 0.035 as a decimal. We are compounding monthly, so n equals 12. Our effective annual yield formula is 1 plus r divided by n raised to the power n minus 1. So we'll now substitute in our values that were given to us. Okay. Then we'll enter this into our calculator, giving us the value 0.035566695. We know we need to write this as a percent, so we'll move the decimal place over, which is 3.556695%. But our problem tells us to round to the nearest tenth. All right, the nearest tenth, not hundredth, nearest tenth. So the nearest tenth of a percent is right here. So this would be 3.6%. Okay. All right. So now we need to determine the effective annual yield for each investment, then select the better investment. If rounding is required, round to the nearest hundredth of a percent. Okay. So we are going to determine the effective annual yield, and then we will compare to determine which investment is better. Okay. So in our first one, we'll give this A and this B. Okay. So for A, we have a rate of 4.09%, which is 0.0409, and we're compounded monthly, so n equals 12. For B, we have a rate of 4.1%, which is 0.041, and we're compounded quarterly, which is 4. Okay. So our effective annual yield formula is 1 plus r divided by n raised to the power n minus 1. So for A, in substituting in our values, we'll have 1 plus 0.0409 divided by 12 raised to the power 12 minus 1. This gives us the decimal 0.04167,548. It tells us to round to the nearest hundredth of a percent. So if we move the decimal over 2 and then round, we'll get 4.17%. Then for B, we'll have 1 plus 0.041 divided by 4 raised to the power 4 minus 1, which gets us 0.04163469. Raised to the nearest hundredth will be 4.16%. Okay. So which one would be the better investment, yield the highest return? This one. So this is the better investment because its return is higher. Okay, just by 0.01%. But still, that's money on the table. All right, that concludes section 8.4.